Okay, so welcome to this keynote speech for the Telecommunication and Signal Conference 2023. This is a virtual conference, and I would like to express my gratitude to the committee members of the conference for inviting me for hosting this keynote speech. I am Professor Francesco Benedetto from the University of Roma, and today the title of my speech is Cognitive Radio Communications, Dynamic Spectrum Access, and Standardization Activities. This is done because here you can find some contacts if you would like to send me some questions or curiosities. I'm at the University of Roma, the chair of the machine learning and data processing, and in particular, I'm also here as the chair of the definition and concepts for dynamic spectrum access. So I'm the chair of the working group of the IEEE 19.1. That is a working group that is working on the revision of the standard on dynamic spectrum access. Well, in my presentation, I would like to show you some key points about cognitive communication, starting from what we are living now, meaning the information era and the big data era that we are now experiencing day by day. Then I would like to have a quick talk about the problem of radio spectrum scarcity, because radio spectrum, you know, is a very scarce resource and must be useful, employed to allow any services to communicate. And here comes the cognitive communication that promises to solve the problem of spectrum scarcity. The enabling technology is the dynamic spectrum access. And in particular, inside the dynamic spectrum access, we will talk about the cognitive cycle and how a cognitive rate and a cognitive system works, but especially we will focus on spectrum sensing. That is the part of the cognitive cycle dedicated to the sensing of the spectrum. Then I will introduce you some activities that, in terms of standardization, that are carried out at a national and international level for all the standardization body, including the IEEE, that I am honored to chair since 2013. And I will briefly conclude my presentation, highlighting some future directions for the next years that have to come. Well, let's start with what we intend with the information era and big data era. There was an important famous sociologist that studied mass media communication. His name was Alvin Toffler. That in a book that he published some years ago, he identifies the times that we are living as the times of the third wave. And in particular, he said that change is a process by which the future invades our lives. But what does he mean with the third wave? Well, let's have a look in details. The third wave is the third technological transformation that we are experiencing today, following the first wave that started with the nomadic era and ended when humans discovered the agricultural, and so we moved to the agricultural era, and then start the second wave until the industrial era, so a couple of centuries ago. What I would like to note here is that from one wave to another, so from the first wave to the second wave, millennia have passed. From the second wave to the third wave, centuries have passed. And from the second wave to the third wave that we are now living, decades have passed. And it's likely that we will have a fourth wave in the next future, since cyberspace technologies are shifting human history from a linear and continuous development to a non-linear and discontinuous progression. See here that the progression is exponential, no more linear. And this progression widely indicates that the world we live in will never be the same. And unfortunately, I have also to underline that we are also living the post-pandemic world. So we have another great discontinuity in our world, that is before and after the coronavirus explosion. What does it mean in terms of communications, and in particular in terms of future mobile data usage? Well, here on the left, you have the estimation of global mobile traffic per month from 2020 to 2030 in exabytes. We have real data until 2023, and then we have estimation until 2030. You can see that the traffic, only mobile traffic, is exponentially growing, is exploding until 2030. And look that we are speaking in terms of exabytes. You all know what an exabyte is, obviously, but let me just underline this interesting comparison. If 1 gigabyte, if we can compare 1 gigabit as the size of the Earth, then 1 exabyte can be compared to the size of the Sun. So this is a very interesting comparison, because even non-technical people can immediately understand how is exploding the mobile data usage. And the same we can say for the number of interconnected devices worldwide, because we are now living not only the big data era, but as well as we are living the Internet of Things, the real Internet of Things era. Because look at the slide on the right. Again, we have real data until 2021, and then we have estimation from 2022 to 2030. These are the numbers in billions of interconnected devices worldwide. Okay, so we will expect in 2030 almost 30 billions of interconnected devices. This is incredible. And let's have another examples that would be very easy to understand why we are living the big data era. Look at the slide on the right. These are the things that happen on internet every 60 seconds. So let just me move my image upper. What happens on the internet every 60 seconds? We have, just looking at the search, the number of searches on Google, we have almost 4 million, 3.8 million of searches on Google. We have more than 350,000 tweets sent on Twitter, or more than 400 hours of videos are loaded on YouTube, and around 700,000 hours of videos watched. Look at Skype. We have more than 2 million minutes of calls done. And the same can be said for all the other services on the internet. So we have a huge amount of data. big data that are also heterogeneous. And in order to account for this kind of data, we need an evolution in the communication technology. In fact, we are now experiencing what we can do with 5G technology, but we are still now thinking and working from now many papers on the IEEE Export databases, delineing what we can do with the 6G technology. That would be the technology of the future. And here you can have a look at the size on the generational leap from the first generation of mobile communication to the fifth generation, or 6G now. So we are moving to another revolution in communication technology, where we demand new spectrum and sell less networks, because we need service added values, and we need a new word that is coming, that is metaverse. And 6G is vital in achieving the metaverse vision. But this implies not only fun and games, but also issues, problems that can be solved, obviously. And here comes the radio spectrum scarcity issues. Because if we need to allocate and communicate all the data that I have talked about just in the previous slides, we need spectrum. But unfortunately, spectrum is a scarce resource and is almost occupied and allocated for existing services and existing standards of communication technologies. Here you can see that the radio spectrum that is here magnified is almost fully allocated to different services, starting from the low frequencies that can be used for radio communication to the high frequencies that can be used for satellite radio communications. But is this problem a real problem? Well, surprisingly, the answer is no. It is not a real problem. But why? Because the spectrum occupancy, some measurements that had been done first in USA and then repeated in Europe, demonstrated that spectrum occupancy is in the range of 15–80%, with a mean spectrum utilization that is lower than 20%. This means that on average, the frequencies that we allocate to various services are used only for the 20% of the time. This means that they are underutilized, and that the spectrum scarcity is the result of a bad allocation of frequencies, of a bad, not efficient use of frequencies. Look at the measurement in some cities. Let's start with the USA, and in particular with Chicago, where, according to a paper of 2011, published in the DICE conference, the mean spectrum utilization is about 14%. Oh, sorry, it's about 14%. Unbelievable in Chicago. And then someone else repeated these measurements of spectrum occupancy also in Europe. And here we have a paper that measures the spectrum occupancy in Barcelona, where the mean spectrum utilization is under 18%. In a city, in a big metropolis, in a very huge city like Barcelona, we have a spectrum occupancy that is under 18%. This is according to paper published in the Vehicular Technology, in the IEEE Vehicular Technology Conference in 2009. Other measurements in other European cities, we have in Brno a mean spectrum utilization that is about 6.5%. And if this is quite a surprise, look at what happens in Paris, in the suburban and urban zone of Paris. We have a mean spectrum utilization that is under 11% in Paris. And these is according to the Crown Code paper of 2010. So this means that we have, by means of the static allocation of spectrum frequencies and spectrum bands that we are performing right now, problems that reflects in radio spectrum scarcity. That is a false problem because we are using inefficiently those frequencies, because we are use those frequencies with a mean spectrum utilization that on average is under 20%. And here comes the cognitive communications solution that promises to be a very powerful solution to, at least in the meanwhile that the static allocation evolve in a more dynamic manner, promises, as I said, I was saying, to be the real solution for the next future, at least for the radio access for new communication standards. But what are cognitive communications? Cognitive communications are communications in which we have a primary user, that will be a user that has paid a licensee to use the frequency, that is using that frequency in a non-efficient way. So he is underutilizing the spectrum band. And so we can have a secondary, one or more secondary users that are advanced technological users that can dynamically access the radio spectrum when the primary user is not using it. So when there is an opportunity to transmit, we can call it a white space. The secondary user can access the radio spectrum with a vinculum to move out from that frequency bands in case the primary user will come back. So we are now going very fast towards a new technology that is fostered by the problem that we have spectrum scarcity. Spectrum scarcity that is due to a static spectrum allocation policy, that is due to the fact that spectrum is a scarce resource, and that is due to the fact that there is a big increase in spectrum demand. So we can dynamically access the spectrum and opportunistically access the spectrum, because we can sense the channel, and more generally we can sense the radio environment. We can learn, providing a secondary user radio equipment with cognition capabilities, and so artificial intelligence embedded in radio. We can provide those radios with the possibility of detecting the radio environment in order to find idle channels. Those cognitive radios has radio awareness. That means that they have awareness of the radio environment in terms of number of users, of type of users, and so they know where and when they can dynamically and opportunistically access the spectrum. So we are moving with cognitive radio from a static spectrum allocation to a spectrum sharing strategy and dynamic access to the spectrum resources. So look at the image on the right. In particular, mobile frequencies are now getting crowded. But with cognitive radio, you can use any channel you want. This can be done allowing cognitive or secondary users to access the spectrum dynamically and opportunistically. However, those secondary users are unlicensed users. In fact, they exploit spectrum holes or white spaces without interfering with primary users' communications. And hence, they can create cognitive radio networks. However, you can easily understand that this poses completely new scenarios in communication technologies now, under the point of view of contemporary communications with primary users. So we can have communications, we say that we have overlay communications, that is meaning that secondary users can communicate in the presence of primary users, but with a power that is under the noise floor, or we can have the opportunistically access, so the underlay access. So secondary users are allowed to access the spectrum only if the primary users are not using it. And then, secondly, just think to all the new cyber attacks and threats that these new advanced technological users, secondary users, can bring in the network that is hosting also the communications of primary users. So we have, as you can imagine, a lot of challenges to face with in the next future. Some are studied a lot in the literature. Some need to be to find some answer still. How secondary users can access opportunistically and dynamically the spectrum that is not used by primary users, by having cognition capabilities inside the radio equipment. What is cognition? Well, as the chair of the IEEE working group 1900.1, I have to say that finding a definition of cognition was one of the hardest issues that we faced with, because it's not easy to understand what cognition is for humans. A nice definition is the one here reported, that cognition is intended as the process of acquiring knowledge and understanding through thought, experience, and sensing. And the key transformational technology in a cognitive system is the ability to learn from observations of the radio environment. In fact, in the published standard in April 2019, we decided to build the basis of the definition of cognition, considering the following attributes as the fundamental blocks of its definition. And in particular, we have considered the capabilities of memory and reasoning, of learning, obviously of goal-driven and adaptiveness. In fact, after 6 years of revision of the standard, we successfully published the new standard with the new definition of cognition. And in particular, we published a definition that says that cognition is the ability to acquire and apply knowledge and to reason based on that knowledge within a given scope to reach a certain goal or objective. Hence, a cognitive radio is a radio that exploits cognition to control its behavior, by means also of a cognitive process. What is a cognitive process? It's a series of actions which as a whole build an essential constituent of cognition. Note that in order to be cognitive, a system doesn't need to be composed by a certain number of cognitive radio, because cognition can be distributed in the system or can be allocated in just one radio, and the cognitive process can regulate the behavior of that system. Hence, that system is a cognitive system. Which are the steps that are performed under the definition of cognition in order to extract knowledge from the data and to reason based on that knowledge? Well, we have here on the right side of the slide the I think you know it is the basic scheme of the cognitive cycle, originally published by Mitola almost more than 20 years ago now. That is the observe, orient, plan, decide, act cycle. So the cognitive radio observe the data coming from the outside world. Then the cognitive radio processes the data and move from the state of observation to the state of orientation. In the orient state, the cognitive radio establishes some priority, normal, urgent, or immediate, and then decides to move to the plan step, to the decide step, or directly to the act step if the priority is immediate. If the cognitive user has time, I mean the primary user is not coming back to exploit the radio spectrum for which he has the licensing, the cognitive radio can plan the action, then can decide which is the best action in terms of the best waveform and the best channel to access, and then he can act. Otherwise, if he doesn't have time, he directly moves to the decide state based on previous planning, or directly on the act step. Note that in the observation step, in the plan step, and in the decide step, the cognitive radio learn, meaning that he improves cycle by cycle, step iteration after iteration, its awareness of the radio environment. So the cognitive cycle is based on the capabilities of the artificial intelligence to provide cognition to the cognitive radio. And the artificial intelligence here becomes the enabler for cognitive self-organizing future networks. As humans perceive what happens around them, and then they reason about those perceptions, combine those with previous perceptions and draw conclusions in order to act and reach a certain objective, a cognitive network will work in a completely similar way, using the capability to observe, reason, and as I said before, act accordingly for a goal-driven. So from the external world, we can have a simplified version of the cognitive cycle that is here represented in 4 steps, or we can say the 4 fundamental operations performed in a cognitive radio, that are the sensing operation, so sensing of the spectrum, the analysis of the spectrum, the decision taken on the basis of the analysis, performed before, and then the action. And so this is continuously repeated. Well, here today in this keynote speech, we will focus in particular on the sensing operation, the spectrum sensing operation, because, well, we know that all these four actions are fundamental actions for the correct working of the cognitive radio, but obviously the first one, that is spectrum sensing, let's say that is the most important one, since it's the step by which everything starts. So if we are not able in understanding if a primary user is present, we cannot start all the further analysis and steps. And above all, if we have an error in the sensing phase, saying that the primary user is not present when instead he is present, this is dramatically disruptive for the system, because we generate a disruptive interference for the cognitive user, but also and above all for the primary user that has the highest priority to communicate on the channel, because he is the licensed user. So let's have a look at the dynamic spectrum access, and in particular to the spectrum sensing technologies that are published in the literature in the last years, and in particular what we have published with the help of my collaborators in my signal processing for telecommunications and economics lab at the ROMA Trade University. As I said before, dynamic spectrum access includes four main functions. Once again, spectrum sensing, and here we have also practical and quick definitions for these functions. So we have spectrum sensing that is quickly defined as the periodical sensing of licensed spectrum in order to identify spectrum holes. Why we are identifying spectrum holes? Because spectrum holes are the represent the transmission opportunity, because in absence means that the primary user is not present, and so we can communicate, we can opportunistically exploit those spectrum holes. Or white space. Then we have spectrum decision. That means that the sensing information is processed, and collected to make decisions. Finally, we have the last two operations that are called spectrum sharing, because after a decision has been made, spectrum holes may be accessed by multiple secondary users, so they have to regulate their power to the minimum level in order to maximize the sharing between all the users. But the cognitive cycle, and so the sensing and the decision must be iteratively continued, because we must implement spectrum mobility, because the secondary users change the frequency of operation, must change the frequency of the operation if the radio environment has changed, meaning that the primary user is coming back, or it has come back and is using the spectrum that is no more a spectrum hole. Okay, so let's have a look in details at the spectrum sensing, and so let's introduce some mathematical notations. I have taken the mathematical notation at a minimum in this keynote speech in order to avoid to annoy you, but some mathematical notation is needed for understanding the functioning of the system. So let us considering the useful primary signal, which is assumed to be affected by additive complex wide Gaussian noise with zero mean and a particular variance. we can express all the signals in terms of their representative vectors. And so we can have the vector x that is represented as the sum of the signal vector plus n. This vector is sampled at the receiver side with a sampling period. And one of the conventional detector that is used in spectrum sensing for cognitive radio is the energy detector. In fact, the decision about the presence of or absence of the signal of interest in a certain frequency band can be obtained by comparing a decision metric, in the simplest case, the energy of the received signal, against a fixed and predetermined threshold. So, in this block scheme, we have the received signal, that is the sum of noise and useful primary signal, that moves into the bandpass filter, into a squaring device, into an integrator, and then the energy is compared with the threshold. This process is equivalent to discriminating between two alternate hypotheses. So we have a binary hypothesis problem, a conventional binary hypothesis problem, as we had in the radar scenarios. We have the H1 hypothesis, which states the presence of the signal of interest, so the primary user is detected because it's present in the scenario, or the null hypothesis, the H0 hypothesis, which conversely states the absence of the signal. So a spectrum mole is detected. So the test, in case of the energy detector or energy detection, is as follows. If the energy is under a predetermined threshold, the primary user is supposed not to be here, and so we have a spectrum mole. Otherwise, if the energy of the received signal is over a predetermined threshold, the spectrum mole is not detected because the primary user is present and is communicated in the spectrum. Well, the threshold is usually evaluated according to an optimal criterion, and in particular, the constant false alarm rate procedure is usually employed for this kind of test. Unfortunately, in the conventional energy detector, this procedure needs to exactly know the noise variance value to correctly tune the optimal threshold. Obviously, exact knowledge of noise variance is usually not possible, and the noise variance is usually estimated, or better, is assumed to vary in a range that is named noise uncertainty, where a parameter rho defines the size of the uncertainty and is usually expressed in dB units. So in the results that I will show you later, we will have all the results in terms of this noise uncertainty. Well, the energy detection or the energy detector has a lot of advantages because it's a completely blind technique and is characterized by the lowest computational complexity at the cognitive receiver side. And this is why the performances of novel spectrum sensing techniques are usually compared to the ones of the energy detection. Unfortunately, the energy detection has also some drawbacks. In fact, it drastically reduces its efficiency at low signal-to-noise ratio values and in presence of noise uncertainty that is usually present in conventional operative cognitive radio scenarios. So let's see what we have done in recent years and in recently published papers to improve the performances of spectrum sensing without increasing too much the computational complexity of the proposed methods. Well, we have started in 2016 by proposing a paper published in the IEEE Communication Letters that considers spectrum sensing for constant modulus signals. We know that constant modulus is just a particular family of signals. And this is the unique assumption we made in our work. We assume that the primary signal is a constant modulus signal. We know that this assumption is quite limiting, but we have to say that is satisfied in many important applications in cognitive radio communications, since primary transmissions usually take place by means of constant modulus waveforms. Then we defined a normalized variance, that is the ratio between the fourth order moment and the squared second order moment of the received signal. Here, you can see. This is done because the rationale of our idea is that when we have the presence of a constant modulus primary user signal, the normalized variance is lower when the primary user is present, so in the H1 hypothesis, while it's higher when the primary user is not present, so in the null hypothesis, when we have only noise. This is because the primary user signal is a realization of a constant modulus process with a certain power. But the same consideration does not apply for the channel noise. Hence, the normalized variance can be the metric that can be exploited for discriminating between the presence and absence of the signal of interest. And this new metric that is comparable to the energy of the energy detector, so we can say that this meter that we have proposed is that an improvement of the energy detection belongs to the energy detection family detector, can obtain better performances without increasing so much the computational complexity of the signal. The only thing that we have to do is that we have to apply this method blockwise. In fact, the primary signal level may be very weak at signal samples in the presence of noise uncertainty, and especially in the presence of channel fading. So we need, firstly, an integration operation in order to elevate this signal level. In fact, we divide the received signal in a number of blocks composed of a number of samples. Then we estimate the second and fourth order moments of each block and evaluate the normalized variance of each block. The normalized variance over all the blocks, over L blocks here, is derived as the sum of the blockwise normalized variances, and then it's used as the testing variable to state and discriminate between the presence or absence of a primary user constant modulus signal. The performances that we obtain for this method are impressive, especially increasing the noise uncertainty. We have here plotted in red the curve referring to the ideal energy detector, where we have exact knowledge of the noise variance and we have no noise uncertainty. So let's consider this red curve as the upper bound of the system, of the theoretical bound, obviously. And then here we have in green the curves referring to the conventional energy detector method, while here we have the curves referring to the new methods, especially proposed for constant modulus signal. We can see that even in presence of noise uncertainty and varying the number of blocks and the number of samples over which the normalized variance is estimated, the performances of our methods remain stable, while the performances of the energy detector degrades rapidly in terms of noise, in the presence of noise uncertainty. Finally, we have also compared these two methods in terms of mean detection time. That is the time on average, needed to declare a correct detection of a primary user. The equation by which the mean detection time is evaluated is here represented. And so if the mean detection time is over 1, this means that our method is faster than the energy detector to perform a correct acquisition. Otherwise, if the mean detection time is under 1, this means that our method is slower than the energy detection. As we can see, our method is the mean detection time is always higher than 1, even varying the number of blocks over which the normalized variance is estimated. So these results show that the proposed method that we have tuned for custom modulus primary user signal is characterized by higher detection probabilities and faster sensing time than conventional detectors, with a negligible increase of the computational complexity, because still we have, let's say, a modified version of an energy detector. Obviously, you can say that this is very good, but it works only for custom modulus signals. So, in a recent paper, dated 2018 and published on the IEEE transactions on vehicular technology, we completely removed the custom modulus assumption, considering the primary user signal now to be as general as possible. Well, in the following analysis, we only assume that, as happens in any communication system, the primary signal is a constant energy signal. This means that even if each sample of the signal has a different power, the energy of each data block composed of n samples is the same and constant for each block. And this must be true for all the communication systems. Well, the rationale of our procedure is that in the presence of such constant energy primary user signal, the series of the energy evaluated over the received blocks of data is characterized by a lower variance, not a lower energy, but a lower variance when the PU is actually present. This means that if the primary user signal is present, the energy series has a low variance in respect to the case where only the noise is present. That's because noise is chaotic, so noise varies a lot, and so has a great variance than in the case of PU signals, that is man-made signal, and so is they have a constant or almost constant variance, let's say a lower variance of the energy. And that's because even if the PU signal is as general as possible, it can be considered as a realization of a constant energy process with constant energy for each data block. But the same consideration does not apply for the channel noise. Hence, the variance of the series of the received signal energy over a certain number of blocks, obviously, can be effectively used for discriminating between the presence and absence of the signal of interest. And here we have the test. Here we have the testing variable, that is the variance of the energy series received at the cognitive receive side. If the variance is greater than the threshold, we have only noise. Otherwise, if the testing variable is lower than the threshold, we have the presence. We detect the presence of the primary user. So again, let's have a quick look at the performances of the method. Again, once again, we have the upper bound here, that is, or lower bound in the sense that we cannot have better performances than the ideal conventional energy detector without noise uncertainty and with perfect knowledge of the noise variance. And then we have the performances of the new constant energy method. And we have also here plotted the performances in the presence of constant modulus method, but applied in non-constant modulus primary user signal. So the method completely fails, as you can see in terms of detection probabilities. The same can be repeated in the presence of noise uncertainty, varying the number of logs and samples over which the noise variance is estimated. And we can see that even if the performances of the method decreases, they are always better than the one provided by the conventional energy detector. And once again, the same is for the mean detection time gain as before. The computational complexity requested by the new method is once again negligible. In fact, the energy detector metric can be obtained with a total of 2n operations, while the constant energy method that we propose needs a total of 2n plus 2m operations. So we have only 2m extra multiplications, but in parallel processing, the 2m extra multiplications can be performed as a single operation, and the complexity of our method can be drastically reduced and compared to be the same of the energy detection. Finally, I would like to quickly show our recent advanced results obtained in satellite cognitive signals. And in particular, in 2021, in February, and then in December, we have published two works, the first one in the IEEE Communication Letters, the second one in the IEEE Networking Letters, referring to higher order moment-based spectrum sensing method for cognitive satellite communication. And in particular, here on the left, we have the representation of the system model of geosatellites and non-geosatellites that are considered as the secondary users in this schema. And this is, to the best of our knowledge, the first spectrum's higher order moment spectrum sensing method that allows fast and reliable detection of the geo signal, considered as the primary user signal. Then we have also proposed a higher order moments-based spectrum sensing method for detecting unauthorized accesses in underlay cognitive satellite communication networks. We can have again a quick look at the performances obtained in both the two papers in both cases. And once again, we have plotted the for reference the performances obtainable with the ideal energy detector, and we can see that our method outperforms the conventional energy detector in many scenarios of interest, and again allowing fast detection. So we have a mean detection time gain that is always superior than 1. The same happens for the paper published in the IEEE Networking Letters. The results have shown that the proposed methods, hence, are characterized by higher detection probabilities and faster sensing time than conventional detectors, thus proving to be very effective for cognitive satellite communications. Okay, now that we have had also a technical look on how performing in a more efficient way the spectrum sensing phase, let's have, before going to the conclusion, a quick look at what is the standardization bodies at national and international level are doing in this world. Well, you know that we have a lot of standardization bodies at national and international level. You all know the IEEE, the ITU, the ETSI, the IETF, and so on, the European Commission, the FCC, etc. Well, let's start with the IEEE. The IEEE has a working group, that is the IEEE 1900.1, that is the working group on definitions and concepts for dynamic spectrum access, terminology relating to emerging wireless networks, system functionality, and spectrum management. Well, the baseline standard was published on September 2008. Then one amendment of the baseline standard was published in January 2013, namely the .1a standard. And the first revision of the baseline standard and of the amendment was published in April 2019 under my guidance. But I have to say that since 2020, so less than 1 year after the publication of the new standard, we have been concentrating on preparing a root and branch revision of the currently published standard that was published in 2019. This is because we will provide an up-to-date viewpoint on the associated fast-moving technology areas. And in particular, we are discussing, and you are welcome to join me in the efforts of producing this revision of the standard in the group. We are discussing about artificial intelligence, as I said before, the cognition capabilities and machine deep learning methods for cognitive radio networks. Then we have other efforts in other standardization bodies. For example, the ITOR has activities that are aimed at providing an enabling environment for the sustainable development of radio communications. And in particular, the ITOR produce recommendations for possible deployment of dynamic spectrum access-based technologies, in particular in TV bands, although spectrum regulations are done on a national basis. And here you can have the most important recommendation that the ITOR published. Other standardization bodies that are focusing on dynamic spectrum access are the ETSI, the ECMA, and the IETF. Even if I have to say that their efforts are concentrated in particular on the television white space. So they have a narrow band focus in respect to what I have talked before. On a national level, well, we had different behaviors coming from different countries. Obviously, USA with FCC and National Telecommunications and Information Administrations are very active in the field of dynamic spectrum access. And here we have the most important documents and recommendations published since 2004 from the FCC in the field of dynamic spectrum access. Europe is another country that is very active with the European Commission that has proposed a series of initiatives designed to establish the right conditions for the necessary investments to take place. And in particular, the European Commission proposed the key principles for spectrum assignment in the Union. And they promote a consistent approach to coverage obligation, small cell deployment, and network sharing, thereby stimulating 5G and hopefully 6G deployment and rural connectivity. And here you have the most important document published in 2016 by the European Commission. Again, we have a lot of efforts in the Asia Pacific region. And one of the pioneering dynamic spectrum regulatory standardization activities in the Asia Pacific region come from the IMDA, that is the Singapore spectrum regulator. Once again, in particular, focusing on the TV white spaces technology to facilitate adoption and to lower cost barriers for the industry. It's worth noting that most countries in the developing world, including Africa, are still lagging behind on the regulatory front pertaining to possible deploying approaches for DSA cognitive radio technologies. However, there is an exception. It is the one from the Information and Communication Technology Authority of Mauritius that published two important documents, one on 2010 and the other one on 2012, regarding the adoption of dynamic spectrum access methodologies. Well, I think it's time now to move quickly to the conclusion of this keynote speech. I have to say that we hopefully have understood that we need clear deadlines for when the spectrum is to be made available to the market, because new services are waiting and the big data are exploding in our information era. Investors in the next generation of wireless broadband need more predictability and consistency regarding future licensing models and the key conditions for assigning or renewing national spectrum rights. They need a minimum license duration to ensure returns of investment, a greater scope for spectrum trading and leasing, and consistency and objectivity in market-shaping regulatory measures. On the other hand, operators should commit to use the spectrum assigned to them effectively, trying to avoid the spectrum scarcity problem that we have talked about at the beginning of this talk. Let me say that the shared use of spectrum, either on the basis of general authorization or individual rights of use, can enable more efficient and intensive exploitation of this scarce resource. And this is particularly relevant for the new very short millimeter spectrum bands foreseen for 5G communications. So what about future directions? Let's say that the technology enablers towards 2030 are as follows, in particular, data-driven operations, distributed intelligence, continuous learning, intent-based automation, explainable and trustworthy, let me repeat this, trustworthy artificial intelligence, and obviously cognitive system. Okay, I would like to thank you all for your attention. Once again, I would like to thank the chair of the TSP conference for inviting me and the committee members. And if you have any question or curiosity, please do not hesitate to contact me. Here you have my emails. And once again, thank you very much for your attention.